Antiderivatives. Alright, so before we look at the formal definition of an antiderivative, let's take a look at a motivating question. Suppose you were given a velocity function, v of t equals cosine t, and asked to find the position function s of t. So this is backwards of what we've been given in the past. In the past, we've been given some position function and then asked to take its derivative to get to the velocity function, and then maybe even take the derivative again to get to acceleration. So this is sort of the opposite idea. We've been given v of t, which is the same as s prime of t, is the cosine function, cosine t. And we're asked to find the position function, s of t. So what would we need to take the derivative of to get to a velocity function cosine t? Well, hopefully a lot of you are thinking, this is the sine function, sine t, that I need to take the derivative of to get to a velocity function of cosine t. Well, if you were thinking sine t, then you guessed correctly, and what you just did was find an antiderivative. So these are the types of questions that are going to come up, but we want to be able to define an antiderivative formally here. So a function big F of x is an antiderivative of little f of x on the interval from a to b if big F prime of x equals little f of x for all x in AB. So this is saying if we take the derivative of big F of x, then we're going to end up with little f of x. So it's exactly the same concept that we did here in this very first problem. What did I need to take the derivative of to get to cosine t? Well, I needed to take the derivative of sine. So that makes sine t an antiderivative of cosine t. So now what we're going to take a look at is, notice here this word is very, very important. A function big F of x is an antiderivative. So does that mean that there can be more than one? So let's think about this for a second. Is there any other function I can take the derivative of and still get cosine t out? Anything other than sine? Is there any other function besides sine t that I can take the derivative of and get cosine t? So the answer is yes, there is actually another function. And in fact, there are infinitely many functions I could take the derivative of and get out cosine t. So let me give you an example of one. An example of one will be sine t plus 1. So remember that the derivative of any constant is 0. So if I said the position function was sine t plus 1, well then its derivative is cosine t plus 0, but of course we don't write that, so this is another option for the position function. So we can do that and create infinitely many options if I just change the constant every single time. So sine t plus 2, sine t plus pi. So the constant doesn't matter. In fact, it could be a negative, so it could really be sine t minus 4. All of these are different variations to give us a more general answer because sine t can vary by some constant. So that brings us to a next definition. So the next definition is that of the general antiderivative. So we're going to let big F of x be an antiderivative of little f of x on AB. So as in the previous example, an antiderivative to cosine t was sine t. Then it's true that every other antiderivative on the interval from a to b has to be of the form big F of x plus c for some constant c. So in other words, all of the different other antiderivatives are going to be almost the same. They're just going to vary by some constant, and it could be any constant. So this plus c can be any number at all because the derivative of a constant is 0. So that's going to be the focus really of the remainder of this chapter's worth of material, is finding out about general antiderivatives and a couple of other topics. But there's this process of finding an antiderivative, and it's called antidifferentiation or integration. So integration, you might be remembering that word from the beginning of the semester when I mentioned that in AB calculus we were going to look at two main branches of calculus. We were going to look at differential calculus and integral calculus. So now that's the portion that we've reached. is integral calculus. So, in fact, an indefinite integral is a general antiderivative. So, a general antiderivative is also called an indefinite integral. So now we're going to start introducing some new notation for an indefinite integral. So the indefinite integral notation is given for us here. So instead of being asked in words to find the general antiderivative, the notation for that is going to be this integral sign here. So it looks like sort of this elongated S. So this right here is our integral sign. Now this function here, little f of x, is what we're trying to figure out. Well, what do I have to take the derivative of to get to little f of x? And this little f of x here is called the integrand. Now the dx, this portion here, is called the differential. And of course, f of x plus c, as we just mentioned, is the general antiderivative, or the indefinite integral. So this portion here is the general antiderivative. So just to sort of look at and talk about the notation and the terminology for the notation, because we're going to be using it quite often for the remainder of this chapter. So now let's go ahead and move on. So the remainder of this lesson is going to be spent on thinking about how to undo all of those derivatives that we went through a whole process of finding in the first couple chapters in calculus. So here, we're going to have a power rule for integrals. So we need to figure out how exactly we are going to undo what we did using the power rule for derivatives. So here, the power rule for integrals says that if I want to find the general antiderivative, or the integral of x to the n dx, well, the power rule for integrals is going to say that I now need to add 1 to the exponent and then divide by that new power. And of course, every antiderivative in this section is going to include that constant plus c. So n has to be a real number, but n cannot be -1, and we'll see why towards the end of this lesson. But n cannot be -1. So our power rule for integrals, we add 1 to the power and divide by that whole new power. So if we sort of think about the power rule for derivatives, we took that exponent and we multiplied, and then we reduced the power by 1, so we subtracted 1. So now instead we have to add 1 and divide, instead of multiply and subtract 1. So we'll see the power rule for integrals in play right now. So let's take a look at an example. This reads, I want to take the integral of x squared dx. So here, I'm going to include an intermediate step that we definitely won't write every single time, but just to show the power rule being done in detail here, we're going to add 1 to the exponent. So I have a base of a variable, I have a number as an exponent, so I'm going to add 1 to that exponent, and then I'm going to divide by that whole new exponent that I created. So x to the 2 plus 1 over 2 plus 1 plus some constant c. So let's go ahead and simplify this. This can be written as x to the third power over 3 plus c. This is a perfectly acceptable answer, or we can write it as 1/3 x cubed plus c. So we can go ahead and imagine the 1 in front of the x cubed and then bringing the 1/3 constant to the front. So 1/3 x cubed plus c is another option. This one's another perfectly acceptable option for the general antiderivative. Alright, let's take a look at a second example. So here I'm going to need the power rule for integrals again. I have a variable in the base and I have a number in the exponent. This time the number is a fraction. So let's go ahead and just show the work step by step here of applying the power rule. So here I'm going to need to add 1 to the exponent. So I'm going to have x to the 3 over 2 plus 1 divided by, and again I'm going to make that new exponent what I divide by. So 3 over 2 plus 1 plus some constant c. So now let's go through the process of simplifying here. We have to add fractions in the exponent. So I'll just go through and show that work. I'm going to have x to the 3 over 2 plus 2 over 2, need my common denominators, over 3 over 2 plus 2 over 2. Again, can't forget the constant plus c. And then finally here I have I have common denominators here, so it's going to become x to the 5 over 2 over 5 over 2 plus c. So here I don't have it quite as simplified as I would like it because I have these two fraction bars here. So instead of writing x to the 5 over 2 over 5 over 2, dividing by a fraction is the same as multiplying by the reciprocal. So I can instead write this as 2 over 5 times x to the 5 over 2 plus c. So this here would be my final answer. So at this step, I wouldn't want to leave my answer with two fraction bars in it. I would instead want to multiply by the reciprocal to get 2 over 5 x to the 5 over 2 plus my constant c. And now let's take a look at another example. I have the integral of 1 over x squared dx. So just like when we took derivatives, we needed to do some manipulation first so that we can apply the power rule. We have to do that same thing here. So before I take an antiderivative, I want to rewrite this as the integral of x to the negative 2 dx. So just looking at the power rule for a second, all we needed was for n to be any real number, positive, negative, it could be irrational, rational, it doesn't matter. It just cannot be negative 1. So my exponent can be a negative, so this is going to work out just fine. And when I apply the power for integrals, I'm going to add 1. So I'm going to have x to the negative 2 plus 1. And then I'm going to divide by the new exponent, so negative 2 plus 1. And I have to remember to add the constant c. So now here I'm going to end up with x to the negative 1 if I add negative 2 plus 1 divided by negative 1 plus c. And I would want to go ahead and simplify this a little bit. I don't want any negative exponents here. And dividing by a negative 1 is just like multiplying by a negative 1. So all in one step, I'm going to write this as negative 1 over x plus c. So I moved that negative to the top here, and I moved x to the negative 1 to the bottom and made the exponent positive. So I have negative 1 over x plus the constant c. So here are my three simplified answers to finding these general antiderivatives, also known as indefinite integrals. Alright, so we have a couple more rules. We have the sum or difference rule. So if I take a general antiderivative of a sum or difference of two functions, that's the same as evaluating each one independently for its general antiderivative. And then we have a constant multiple rule. So just like we had one for limits and we had one for derivatives, we can pull a constant out of an indefinite integral. So here, the integral of k times f of x dx equals k times the integral of f of x dx. So I can pull out a constant k. So k here is just some number. I want to be careful. I cannot pull out a function, anything with an x in it, but I can pull out any number k and sort of just ignore it or leave it there off to the side. So as long as it does not have an x in it, because x is the variable, so here this differential dx tells us x is the variable, anything without an x, just a number, can be removed from the indefinite integral. So let's go ahead and apply both of these rules at once, the sum rule and the constant multiple rule, in the next example. So I want to find the general antiderivative, the integral of 3x squared plus 2x dx. So the sum or difference rule tells me that I can split this up into two separate indefinite integrals. So I can solve the integral of 3x squared dx plus the integral of 2x dx. And now the constant multiple rule tells me that I can go ahead and pull out the constant. So this is now 3 times the integral of x squared dx plus 2 times the integral of x dx. And so now each of these separate integrals can be solved using the power rule for integrals, as in the previous example. So the 3 just kind of stays there, and I'm applying the power rule here to x squared. So without showing the steps as in the previous example, we're going to go ahead and add 1. So I have 3 times x to the third power, so I'm going to add 1 to the exponent and divide by that new exponent. So the new exponent is 3, so I'm going to divide by 3. Plus, and now I'm going to solve this general antiderivative separately, so I'm going to have the 2 just hang out there. And then the antiderivative of x, well here this is an x to the 1, so if I add 1, it's going to become x squared, and then I divide by the new power, and that would be 2. So now the question you might be asking is, over here, when I split this up into 2 integrals, why didn't I put a plus c? And then over here as well. So I don't want to have 2 separate generic constants floating around. Instead, since it's in general anyways, I'm just going to combine them together to become just 1 plus c. So it doesn't matter how many functions we're adding or subtracting to each other and solving separately, we're only going to put 1 plus c at the end of the entire expression here. Because since it's just some generic constant, it doesn't matter if I have a plus c minus d plus e minus g. It's just some generic constant. So we're just going to combine it together as this 1 plus c. So now I should simplify though, because I have 3 times x cubed over 3, so these 3's would cancel out. Whoops, not erase, cancel. And these 2's would cancel. So my simplified answer here would be x cubed plus x squared plus some constant c. And this is going to be the general antiderivative to the original function I was trying to evaluate. So now the really nice thing about integrals, provided you know how to find derivatives, is that you can check your work. So just as a real quick mental check here, I want to make sure that when I take the derivative of this function, I get back to my integrand. So the derivative of x cubed, well, by the power rule, it's going to be 3x squared, plus the derivative of x squared, well, that's just 2x to the first, or 2x, plus the derivative of a constant is 0. So perfect, we did everything correctly. We found our general antiderivative here. Moving on, we're going to take the integral of the exponential function. So this one's a nice one. The integral of e to the x dx is just e to the x plus c. And that should make sense because the derivative of e to the x is e to the x. So the antiderivative of e to the x is e to the x. But we cannot forget that plus c constant because we're taking a general antiderivative here. But this next variation will make a little more sense when we look at an example. So if I have the integral of e to the kx plus b dx. So in other words, I have e to some linear function. So kx plus b is the equation of a line. So I have a composition of functions. So I have e to the kx plus b dx. Well, the antiderivative there is going to be 1 over k e to the kx plus b plus c. So something that we're going to learn is that integrals take a little bit more finesse to solve than do derivatives, because what you might be thinking is there some general rule that will always work when I have a composition of functions to find an antiderivative? And in fact, the answer there is no. So we're going to have a lot of little tiny variations for the different types of problems, and quite a few more rules to solve, in general, various antiderivatives. So the rule for this exponential function raised to with a linear function in the exponent has this particular rule associated with it. And let's go ahead and take a look at why. So in this example, I have the integral of e to the 3x plus 2 dx. So according to this rule, the antiderivative is going to be 1 over 3, because my k value here is the number that goes before the x. So 1 over 3 e to the kx plus b, well, that for me is 3x plus 2, plus my constant c. So you might be looking at this like, why is this a formula? But again, remember, we can always take the derivative to make sure that this is going to work out correctly. So if I think about taking the derivative of e to the 3x plus 2, so let's go ahead and ignore the 1/3 for a second. If I want to take the derivative of this function here, let's bring the 1/3 down. The derivative of e to the 3x plus 2, Well, remember the rule for derivatives of e to the f of x. We just repeat the entire function, so e to the 3x plus 2. And using the chain rule, we multiply by the derivative of the inside. So the derivative of 3x plus 2 is 3. So notice the 3 and the 1 over 3 become 1. So this is going to essentially cancel out, and I'm going to end up with e to the 3x plus 2, which is my integrand. So that's how we end up getting this formula, 1 over k e to the kx plus b plus some constant c, when evaluating an exponential function of this form. So the answer to this one, we can erase that additional scratch work here, is 1 over 3e to the 3x plus 2 plus c. And let's look at some more general antiderivatives, this time of some trigonometric functions. So if I want to take the antiderivative of sine x dx, that one's going to be negative cosine x plus c. So if we think about that for a second, if I want to take the derivative of cosine, I will get negative sine. So I'm going to need this extra negative here to cancel to end up with an integrand of positive sine. So the antiderivative of sine x dx is negative cosine x plus c. This one we did as that motivating question. The antiderivative of cosine x dx, well, that one was sine x plus some constant c. So now here I have the antiderivative of secant squared x dx. So if you remember, I would need to take the derivative of tangent x to get out secant squared x. So that's my antiderivative there, tangent x plus c. If I want to take the antiderivative of cosecant squared x, well, that antiderivative is negative cotangent x plus c. If I want to take the antiderivative of secant x tangent x dx, well, then I have an answer of secant x plus c. The derivative of secant x is secant x tangent x. And then finally, if I want the antiderivative of cosecant x cotangent x, then my answer is negative cosecant x plus c. So you'll notice this really comes down to knowing your derivatives so that you can think about, well, what did I have to take the derivative of to get to this integrand? So let's go ahead and apply all that we've done so far to one example. So I want to find the integral of 2x cubed plus e to the x plus secant squared x dx. Well, my sum rules say that I can split this into 3 separate integrals. But as we said, we're going to end up with just one generic constant, no matter how many things we're adding or subtracting. So instead of rewriting each one of these as a separate integral, I'm just going to look at each one independently, one at a time. So first I want to think about the antiderivative of 2x to the third power. So over here I'm going to have 2, my constant, just stays there, x to the, now I have to add 1 to the exponent, so 2x to the 3 plus 1 is going to give me 4. And then now I divide by the new exponent, 4. So now I've taken the general antiderivative using the power rule of 2x cubed. Plus, now the antiderivative of e to the x, well, that's nice, that one's just e to the x. And then finally, the antiderivative of secant squared x, so we would need to take the derivative of tangent x to get out secant squared x. So my antiderivative here is plus tangent x plus my constant c. So just one generic constant for the entire problem. And I can simplify a little bit here because I have 2 over 4, which will simplify to 1/2. So I can write this as 1/2 x to the 4th plus e to the x plus tangent x plus c. And that there is my general antiderivative. So now looking at some more trigonometric integrals. So this time I have the integral of sine of kx plus b dx. And this antiderivative is going to be negative 1 over k cosine kx plus b plus c. And the antiderivative of cosine kx plus b dx equals 1 over k sine kx plus b plus c. So this 1 over k should look familiar from when we found the general antiderivative of e to the kx plus b. So again, I have this composition of functions where the inside function is linear, and that has a special rule. But again, in general, we're not going to have quite a special rule just as we did for derivatives and the chain rule when I have a composition of functions. So these are two unique cases here that I can apply. And we'll go ahead and look at another example that combines a lot of our properties again. So the example is the integral of 3 over x cubed plus e to the 5x plus sine of 3x dx. So again, we'll just handle each one of these separately. So before I even take the general antiderivative, I'm going to rewrite 3 over x cubed as 3x to the negative 3. So another question you might be thinking is there any form of a quotient rule? And the answer there is no. There's no quotient rule, there's no product rule, there's no chain rule for finding antiderivatives. So this, it does have the form of a quotient, but I want to rewrite it so I can apply the power rule. So I'm going to solve 3x to the negative 3 plus e to the 5x plus sine 3x dx. And now I'm going to handle each one separately. So I'm going to have 3x to the, here I'm going to add 1. So if I add 1 to negative 3, I'll have a new exponent of negative 2. And I divide by the new exponent. So now I've handled the first portion. Plus, now here I have e to the 5x. So this is the special case where I have e to a linear function 5x. So I have 1 over k, k in this case being 5. So 1 over 5 e to the 5x. Now here I want to take the antiderivative of sine 3x. So we're using this variation here of the antiderivative of sine. So 3x is a linear function inside the sine function. So the formula tells me I'm going to have negative 1 over k. So negative 1 over 3 cosine of kx plus b, in this case 3x. And then I can't forget the generic constant c. So really the only simplifying I can do here is with this first term. So I can rewrite this as negative 3 over 2x squared. So I'm just moving x to the negative 2 to the bottom of the fraction bar, and I just put that negative to the top, plus 1 over 5 e to the 5x, and then minus 1/3 cosine 3x plus c. And this is going to be my general antiderivative. If we want to check real quick, we could do so at this stage. It'd be a little bit easier. So if I apply the power rule here, if I bring this negative 2 to the front, well, the negative 2's are going to go ahead and cancel out. So I'm going to have 3x to the, I'm going to subtract 1, so 3x to the negative 3. That works. Here, if I take the derivative, by the chain rule, I'm going to bring this 5 to the front. 5 times 1/5 cancels, and then I'll just have e to the 5x. And then finally, the antiderivative of cosine is negative sine. So the positive here will become the negative will become a positive, and the chain rule will tell me to multiply by the 3, and the 3 and the 1/3 will cancel. So I'll just get plus sine 3x. So this is the correct general antiderivative. And finally, we're going to look at the general antiderivative of f of x equals 1 over x. So if I want the antiderivative of 1 over x dx, which can also be written as the antiderivative or the integral of dx over x, so just going ahead and moving the differential to the numerator, the antiderivative there is the natural log of the absolute value of x plus c, where x cannot be 0, because of course we can't evaluate the natural log of 0. So here, remember, the derivative of the natural log function is 1 over x. So if I want the antiderivative of 1 over x, then we're going to have the natural log of the absolute value of x. So here, in this case, we have to make sure and include the absolute value bars, because we cannot evaluate the log of anything other than a positive number. So let's go ahead and take a look at that in an example. So here, the antiderivative of 3 over x dx. So my constant multiple rule says I can go ahead and pull out this 3. So I'm really being asked to solve 3 times the integral of dx over x, or 3 times, here I have exactly the natural log of the absolute value of x plus c. So now here, this is my general antiderivative. And so let's take a look at this example that combines everything that we've covered so far. So I have the integral of 4 over x plus 2 over x squared plus e to the negative 2x plus x to the 1/2 minus sine pi x dx. So all the variations of the problems that we've solved so far. So here, 4 over x. So right now at this point, I mentioned there was no quotient rule. So your intuition might be to go ahead and start out by writing this as 4 over x to the negative 1. But that's not the right strategy. So here, notice, when I had the integral of 3 over x, so I wanted to think about it as 3 times the integral of dx over x, or 1 over x, because I know that natural log absolute value of x is going to come out as the antiderivative. But because we've been in the habit so far, and on this next one we're going to use this strategy of rewriting the exponent, bringing it to the top and making it negative, we might think that that's the right thing to do here. Now, if you thought it was the right thing to do, 4x to the negative 1, rewrite it like this. Well, here's what's going to happen. If I attempt to use the power rule on this, then I'm going to have 4x to the, if I add 1 to negative 1, I'm going to get 4x to the 0. And then the power rule says divide by the new exponent. Dividing by 0, always bad news. So that should automatically tell me that that's not the right strategy to do for this first term. So let's go ahead and erase that. So the first term we're going to leave as 4 over x. The second term we are going to rewrite as 2x to the negative 2. And then everything else will leave the same as e to the negative 2x plus x to the 1/2 minus sine pi x dx. Alright, so now let's go ahead and solve this. So here we're going to end up with 4, that constant, that we're going to pull out, and we have 1 over x, so the antiderivative is natural log of the absolute value of x. We're done with the first part. Now here we're going to have 2x to the, if I add 1, I'm going to have to the negative 1 divided by negative 1. Now e to the negative 2x, my rule here is going to tell me to have plus 1 over k, k being negative 2, e to the negative 2x. Here I have x to the 1/2, so I'm going to add a power, x to the 3 over 2. So if I add 1 to 1/2, I'm going to have 3 over 2. So now normally I would divide by 3 over 2, but we mentioned instead of doing that, it would be easier to multiply by the reciprocal, 2 over 3. So let's put the 2 over 3 in front. And then finally here, I want to take the antiderivative of negative sine of pi over, or pi times x. So I know that I'm going to have a 1 over pi. That's for sure. So this is my k. So I have to have 1 over k, so I'm going to have 1 over pi. So now I have to remember that the derivative of cosine, just regular positive cosine, is negative sine. So I'm going to want plus 1 over pi cosine pi x plus c. So here the only simplifying that I can really do is leave this as 4 natural log of the absolute value of x minus 2 over x. So I move that negative, go over here, and then put the x to the negative 1 on the bottom, minus 1/2 e to the negative 2x plus 2 over 3 x to the 3 over 2 plus 1 over pi cosine pi x plus c. So as far as antiderivatives go, this is really as complicated as we can possibly go so far with the material that we've covered in this lesson. This is the amount of possible variations we can talk about with the general antiderivatives of 1 over x using the power rule, e to the kx plus b, or the trig functions that we are so far familiar with. So this is really one of the harder problems that has to do with all of the rules that we've covered so far.
Another very important formula, although one students really tend to butcher, is this next one that says if I have the integral of 1 over kx plus b dx. Or another way to think about this is moving the differential dx to the numerator, so the integral of dx over kx plus b. So the antiderivative of this, the integral of this, is 1 over k, the natural log of kx plus b plus c. So I would take that denominator, kx plus b, and it becomes the inside of the natural log function, and then 1 over k comes in front. Oops. And then, of course, plus the constant c. So why do students tend to mess this up? Because this previous formula here only works when the denominator is linear. So that means the denominator has x, or the variable, to the power of 1. 1 only. So this is like mx plus b, or kx plus b, right? X is to the first power. So I have a linear function on the bottom, and that is it. That is the only time natural log comes out, and I can't say that enough. It's one of the things, like when I put it on the top of the board, because you can't say it. This is like one of those rules that's messed up that badly every time, that people just want to say when I see a fraction, oh, it's natural log. No, only when the bottom is linear and that there's nothing else on the top besides a constant is the only time this is going to work. So something like this, I have the integral of dx over 2x minus 3. So I have a linear function on the bottom and a constant, a 1 on the top. So this is 1 over k, so 1 over 2, the natural log of the absolute value of 2x minus 3 plus c. So this one works, or even if there was a number on top, like a 3, that's fine, because I can pull a constant out, and then that would just change this to a 3 in front. But here's when this never ever works, and I'm going to change my pen to red to indicate how horrible this is. Sometimes I have students that say, oh, well, I have dx over the square root of x. Oh, well, there's one thing on the bottom, and then it magically becomes natural log of the square root of x plus c. Don't even write this down, because this is so horribly wrong, and I don't want you to, I almost didn't want to do it just because I don't want it to be stuck in your mind like this. So you cannot do this, and people do it with everything. So when the problems get harder, and they will get harder, and they end up being, I don't know, maybe something like this, and they see just that one thing on the bottom, and they turn it into a natural log of x squared minus 1 plus c. So wrong, because this is an x squared. It only works, and this was wrong because this is x to the 1/2. It only works when the bottom is linear and there's only a constant or a number on the top. So these are horrible. These are completely wrong, and you can never, ever do them. So I almost hesitate to give this formula, because there's another way we're going to learn later called use substitution that allows us to solve this and arrive at this formula. But it does come up often enough that you should recognize that when I have a differential with just a constant over a linear function, that it ends up being the natural log function.
Alright, so let's take a look at some common mistakes. So a lot of students want to apply the power rule to everything. So what they want to do is try to evaluate the antiderivative of any function raised to some numerical power, and they want to apply the power rule where they would add 1 and divide by the new power. That does not work. So notice this does not equal to. This is not a rule. So please, if you're going to write this down, don't write it down with an equal sign here. This is not true. They're not equal. This doesn't work for any possible function. So for an example, a lot of students will see something like this. So I have the antiderivative of 2x squared plus 3 squared. So a lot of students will want to say, well, let me just go, here's a power. I'll add 1 to the power. So 2 plus 1 is 3, and then I'll divide by the new power, add c, and I'm done. Again, notice these two are not equal. So that is not the correct solution to this general antiderivative. In fact, the way that we have to solve this is to distribute. So I have 2x squared plus 3, and this means I have 2 copies of it, so 2x squared plus 3 dx. So what I'd have to do is go through this process of distributing and then apply the power rule to each one. So this is a common mistake that students tend to make, especially at this stage, because these are the only rules that we have so far to try to apply. But in this case, this does not work, and the only way we have to solve this type of problem is to distribute and then solve each portion using the power rule. Alright, and lastly, let's go ahead and take a look at some assorted AP multiple choice questions. So this was a question taken from a previous exam. We have the integral of x cubed minus 3x dx. So notice these are multiple choice questions. Something as basic as this wouldn't fall in the free response portion, but as multiple choice. So this is a direct application of the power rule for integrals. So you'll notice here we're going to add 1 to the power. So we're going to have x to the 4th over 4 minus, and here we have 3x, so we're going to have 3x squared, so we add 1 to the existing one, and divide by the new power, 2, and then we're going to add the c. So taking a look at my possible options, I can tell that e is the answer. I have x to the 4th over 4 minus 3x squared over 2 plus c. So my answer to this first problem would be e. Here we have a different AP multiple choice question. We have the integral of sine of 2x plus 3 dx. So this is again a direct application of what we've taken a look at so far. So the general antiderivative here, we want to end up with a positive sine function after we take the derivative. So the derivative of cosine is negative sine, so I'm going to need a negative in front. My rule says 1 over k, so 1 over 2 cosine of 2x plus 3 plus c. So here it looks like my option is D. So negative 1 over 2 cosine 2x plus 3 plus c is my solution. So to close, I want to focus on a big picture idea, the main idea here, that if I have the derivative of big F of x and that equals little f of x, then if I take the antiderivative of little f of x, I have to get back to big F of x plus some constant. So sometimes the big F little f notation makes it hard to see, and I went ahead and used the same variable with the prime notation instead. So the derivative with respect to x of g of x equals g prime of x, so this is a notation that we've seen in the past, is the same as if I take the antiderivative of g prime of x, then that's got to get me back to the original function g of x. So this is actually a really big concept that we're going to head to in the future, but this is the main idea behind an antiderivative. So if I take the derivative of a function and I get out g prime of x, then when I take its antiderivative, I better get back to g of x. So that wraps it up for the main idea behind antiderivatives.